in recent years, we've seen a tremendous acceleration of deep learning research. But apart from that, we've also seen a tremendous integration of AI into various fields. And at the intersection of AI and mathematics, there is a concept called automated theorem proving. And we will try to convince you that it has the potential to change maybe not the whole world, but the world of science at least. It can do, well, what can't it do? It can verify systems of all kinds, hardware, software. It can verify mathematical proofs. It can verify correctness of cryptographic systems. And, well, what AI can we do to aid it? So this project is exactly that. We try to accelerate or maybe integrate AI into automated theorem proving, which is, well, mathematics, but also much more. The resulting project and the paper you have in front of you, it's called Magnushammer, a transformer-based approach to premise selection, which is authored, among other people, by yours truly and Szymon. And it has been submitted to this year's NeurIPS. We are waiting for the results. Right, so what is automated theorem proving, and what component of it are we concerned with? Let's say we have a very simple problem, just like this one here on the screen. We have a natural number. We have to prove that two functions of this number are co-prime. How does it look in an automated theorem prover? We have a formal specification, which is exactly that, but expressed in this artificial language. And what we would like to do is write a proof for that, because what we have is just the proposition. How one usually does that is come up with different steps that are applied one after another, and the steps sort of refine the proof to make it more and more close to the mathematical axioms. So we sort of simplify it to the simplest elements, I suppose. All right, so let's go over the details. We are concerned with proving mathematical statements. Let's just concern ourselves with mathematics for now, written in a formal language. And there is loads of environments for that. We picked just one of them. And the automation of this process, so not having a human interact with this formal language, has already been sort of done, but without AI, or almost without AI. There is loads of SAT solvers, SMT solvers that help human mathematicians come up with those proofs, but they are, let's say, limited. So the scope of this project is very well defined. We want to be able to recommend the most suitable lemmas for a given proof. So let's say a human mathematician wants to prove a theorem, and he would like to know what kind of lemmas would be useful for that theorem. This is exactly what we try to offer. Right, so let's go over the main concept. That's premise selection. That's exactly what I just told you. We want to recommend the best lemmas for a given theorem. There already exists symbolic methods for that, and we want to beat them. This is one of our baselines. It's called sledgehammer, and it's very celebrated among the automated theorem proving community. The task itself is difficult, for example, for language models, because the context size is huge, and apart from that, when there are new theorems, new lemmas to choose from that the model has not seen in training data, it doesn't seem very attractive to the model, which is, of course, a problem. There have been some machine learning done on this exact topic, not very impactful. Right, let's go over a simple example. We have the formulation of the theorem that I have already shown, and we have a sort of like a function that's called metis that is applied to prove the theorem. and it needs lemmas that I described earlier. And the lemmas are add association, which is like the associative property of addition, commutativity, and some other stuff. Each one of those is a real lemma that was previously proven in this environment, and this is how it looks like. It's already got a proof as well. All right, so this is still me, right? All right. So let me describe the tool that already exists that is symbolic. It's called Sledgehammer, very well celebrated. It can do a lot of stuff. It can handle a lot of like low-level variables. It handles some logics that are used throughout the environment, and it's like pretty complicated. It required a lot of expert effort for the tool to be developed and for it to work. And it just basically shoves a whole lot of lemmas into an environment where it can run different SAT solvers. And if some SAT solver manages to prove the theorem using a subset of those lemmas, it says, all right, so those lemmas are probably useful. But the problem is, when you shove a lot of lemmas into the SAT solver, it blows up combinatorially, right? So the subsets of the lemmas that we can use are finite and not very big in terms of all the possible combinations. So we would like to come up with some good heuristics, and this is exactly what we did. Let's go further. The disadvantages, apart from what I've already described. CPU heavy, quite slow. It requires a strong CPU and optimized for 30 seconds for one try, which is a long time considering that you try a lot of times. It can still solve only just simple problems, like kind of finish an already like well-developed proof. It can do the last step. And it doesn't do well with induction problems, which are pretty common in some branches of mathematics. It can be sort of ameliorated, but fundamentally, it's not very good for that.
Okay, so let me talk about the main challenges for using neural networks for the premise selection problem. So as Shimon explained, it's an extremely difficult task, and you might ask, like, why not just apply, it's like 2023, why don't we apply language models for this task? So one of the main problems is that language models have usually quite small context windows. So if you want to embed like the entire knowledge base of available theorems in Isabelle, even for a particular proof, it's going to take like more than 1 million tokens, we estimate. So the model has no way to access all of those premises. We tried to do some research on like just training a standard language model on proof steps, and it turns out that the models hallucinate the premises a lot, like 98% of proof steps with premises, they don't even parse because they use non-existing lemmas. So let me introduce the Magnushammer. Yeah, that's the hero. So we take inspiration from CLIP, which has been tremendously successful in vision language modeling. So the main idea is just like, let me quickly recall CLIP. So we have two modalities. We have images, and we encode an image into one embedding. And we also encode a text corresponding to this image, so a caption. And we have one common space, one common embedding space where we just compute dot products between those two. And it turns out that this simple dot product similarity has been shown to have like strong semantic power and generalization given the success of CLIP. So in our method, we basically, instead of images and text, we just encode proof states, which are textual representations. like here. One advantage of our method is that previously applied deep learning methods used a lot of inductive biases with respect to those expressions, like they, for example, used graph neural networks, exploiting the fact that most of those expressions are just trees. We don't use any inductive biases, we just apply transformers to those, both the proof state and premise. So we basically encode the proof state and the premise separately in the first phase, which is called select. So we do a thing very similar to clip, and we select top k premises for a given proof state. Let's say k equals 1000. And in the second phase, we re-rank those premises. So it turns out to be important for the underlying automated theorem provers that more relevant premises are at the beginning of the argument list for those. So we have observed improvements by using a second phase called re-rank. So while the first phase just uses clip, so it's like a dual encoder from information retrieval terminology, the second phase is using a cross encoder. So we basically encode both the proof state text and premise text by one model in one forward pass for each of the pairs selected by select. And then we output just one score for each of the pairs, and we re-rank by that.
Right. The data set. We need data to train it, right? There was no existing data set for this task, and what we did is put in a lot of hours and a lot of frustration to mine this data set from the Isabelle, from already existing proofs written by human mathematicians in Isabelle. It's taken a lot of time to develop the code, to test it, to debug it. Debug it is probably like 60% of the time. And it has taken a lot of time to actually mine it. We used a CPU cluster, and it was the equivalent of 17 CPU years to mine it. But we did it. And we liked the data set so much that we decided to make it open source, but that's in another slide. What we did to mine the data set actually is we took all the proofs that were already existing, that human mathematicians wrote, but also we decided to try to generate alternatives of those proofs using the affirmation sledgehammer tool. And it was quite successful, actually. We managed to expand the data set at least 2 times. We were very happy with that result. And we decided to release this data set to the public. It's already getting some traction on both GitHub and on Hugging Face. So if you don't know what to do on a Saturday night, here you have it. It's got, 5 million examples, at least, almost. And it's a very sizable data set. You will see in later slides that it is actually more than enough for at least our use case.
Yeah, so one of the main goals of our project was actually to compare with Sledgehammer, which is a well-celebrated baseline, and actually to beat Sledgehammer. And yeah, what does it take to compare? So basically, we need to measure proof rate. So this is like the solve rate on the test set of PISA benchmark and one other benchmark that we mentioned further. So we need to define a notion of compute budget for a fair comparison with Sledgehammer. And we compared our model against, apart from Sledgehammer, we also used BM25 just to verify that our model does something more than just simple text similarity, because BM25 just, it's an untrainable method that just compares the text of proof state and premises.
It's still very strong, though. It's a good baseline.
Yeah, as you can see. So first of all, our goal of beating Sledgehammer has been reached. So we are very proud of that by a large margin. But also we can see that BM25 is quite strong baseline, but it's outperformed by Sledgehammer, which which shows that Sledgehammer is also a strong baselink. So yeah, this is the single-step setting. So we just evaluate on proofs that can be closed in one step. So here you can see like scaling of those different methods with inference time compute. So as I mentioned, we defined a compute budget, and we can see that we can beat Sledgehammer at a very low budget with Magnushammer, which looks promising because this means we can it's likely that we can use Magnushammer without any accelerators like GPU, just do it on the edge. So one promising step, though, in 2023 is to use Magnushammer as a tool by a language model. So you might know stuff like toolformer. So the idea is to teach a language model that generates normal proof steps. So here I mean models like GPTF from OpenAI to additionally decide if they want to use premise selection in a given step. So yeah, you can see the Tor paper for details, because this idea dates back to the Tor paper mentioned here. So for the entire training corpus, we do the following. We have our proof states, and the language model, we can get the data on whether Sledgehammer can solve the task from this particular proof state. So if it's worth to use premise selection in this state. So that's where our training signal comes from. And if yes, then we teach the model to output a special token indicating that we should try to call Magnushammer or any other premise selection method. So yeah, the results are quite encouraging. So we actually set the state of the art on the PISA benchmark by combining Magnushammer with a language model based neural theorem prover. And we also have quite promising results on mini F2F benchmark, which is a more like well-known formal theorem proving benchmark consisting of high school competition level mathematics. And we can see that we compare pretty favorably to the state-of-the-art methods, although it's worth noting that those underlying language models in the other methods are much larger. Like for instance, DSP uses Minerva and also Codex. So those are like huge language models, while we use very small models like 100 million parameters, which is for today it's like very tiny models. So yeah.
Right. So we see the success. Let's try to explain it. What happened? The first question is related to what I've already told you, is that the dataset size that we managed to mine was big. And we don't need nearly that number to beat Sledgehammer. We can use just what, 0.1% of the data to fine-tune the language model, to fine-tune on clip for it to beat Sledgehammer pretty favorably, because it's already 40%. What else? We investigated whether pre-training helped for the clip model, because you can pre-train the backbone. And it does. Well, it wasn't very surprising, but we were glad to see that there isn't something sketchy going on under the hood. The pre-training helped as it should have. And let's go over. Right, so what's left? What can we do with this success? What we did was entirely in Isabelle, and while Isabelle, the theorem proving environment, is very well developed, it's not very popular anymore. Now, for example, Lean, which is another environment, is getting much more popular. So people, when they go to university, for example, I think in Netherlands and in USA, they often have classes on interacting with those automated theorem proving environments. So if we manage to transfer our method to Lean, we can actually help machine learning, mathematics students get into Lean quickly, which would be very valuable. And there is an ongoing effort on exactly that. I suppose that is all. And if you have any questions, we would be happy to answer them.